Okay, so good afternoon, everybody. So I'm going to give a better, more precise inventory of the instruments that we have here in La Silla and Paranal. So Bruno already showed this slide. So it shows you that indeed in Paranal, we are already many instruments, 3 basically per instruments plus 1 CUDE and VLTI instruments, as well as the survey telescopes. And in addition, we have also in La Silla some other instruments. So when you put them all together, we have really a very amazing suite of instruments. So basically, if you are looking for an imager in the visible infrared with or without AO, you will be able to find them. We have instruments that can do multiplex observations, so multi-spectroscopic observation or integrated field spectroscopy. We have polarimeters on various instruments, again, in the visible or in the AO, and interferometry instruments. And we have also a large range of spectrographs. So here is a plot showing as a function of wavelengths, so going from the optical to the mid-infrared, and as a function of the resolving power. So basically, whatever you need, you can find an instrument that is going to address your science. So and what I'm going to do now is a little bit tedious, and I apologize for that, but it's really going through this and try to say what kind of things we have and what kind of things you can do with it. So starting with the survey telescope, so we have VIRCAM, which is attached to VISTA, which is a 4-meter telescope. And this is a wide field infrared imager, so observing in this wavelength range with a pixel scale of 0.34 arc seconds. And it's composed of a mosaic of 16 CCDs, like that. And so if you do 6 paw prints in a well-defined structural manner, you can cover a field of view of 1.5 square degrees. So it's really a huge area that you can cover. Similarly, we have OmegaCam, which is attached to the 2.6 meter survey telescope, VLT survey telescope, VST. The S there is not for small, okay, it's for survey. And this observes in the visible from 350 to 1000 nanometer. It has a larger, the number of broadband and narrowband filters, and there again contains 32 CCDs in order to cover a 1 square degree field of view. But in fact, this is a wonderful German understatement. This is a German instrument. Because in fact it should really be called a focal reducer, fast imager and low dispersion single and multi-object spectropolarimeter. Okay, so it should be called FORSFISMO. But because indeed this is the Swiss Army knife of Paranal. It can basically do everything except your coffee. So it does imaging, long stick spectroscopy, multi-object spectroscopy, with or without mask, and it can also do polarimetry and spectropolarimetry. So this is what it's using for imaging. It's used to do most of the iconic ESO images. This is the famous Orsett Nebula, which was done at the beginning of the VLT. And this is not the image that was done of the Thor helmet, which was made for the 50th anniversary of ESO. And so forth has a field of view of 7 by 7 arc minutes and a pixel scale of 0.12 arc seconds. So it has also a lot of broadband and narrowband filters. So that's why you can do a lot in photometry and imaging with this instrument. This is a typical limiting magnitude that you have. With force, we have 2 CCD, so one in the blue and one in the red. And depending on which one, you will have different limit magnitude, but basically the limited magnitude is around 27. Of course, this is just a value given for if you observe for 1 hour. You can always do better. This is one example. This is in fact a picture of comet Halley, when it was as far away from the sun as Neptune. And so it has a magnitude of 28.2, and trust me, it's there. And this was in fact observed at the time with 3 telescopes together, FORCE 1, FORCE 2, and VMOS, over 3 nights for a total of 9 hours of observations, which were all stacked together to create this image and to make sure that the comet was still there at the other side of the solar system. We can do long slit spectroscopy with FORCE. This is the parameter, so you can choose the slit between 0.3 and 2.5 arc second, and the resolution is about 150 to 2600. And the magnitude limit is roughly 2324. This is just one example of a very nice planetary nebula, Flaming 1. The image was taken with FORCE, but in addition, we then observed the central star of this planetary nebula and took a long slit spectra of it to measure the radial velocity. And we could discover that inside this planetary nebula, there is in fact a binary system with an orbital period of only 1.2 days. So a very post-common envelope binary, which was a big surprise given the huge jets that were seen there. With FORCE, you can also use multi-object spectroscopy. And in fact, you can design masks and put many slits over all the objects that are of interest in your field. And basically, you can put up to 100 slits. I mean, it really depends on the configuration that you are choosing with various sizes and lengths. And you can also choose among rectangular slits, but also circular and curved slits. So really, only your imagination is the limitation here. So one of the nice discovery from FORCE was that it was able to rediscover life on Earth. So it's always very good to know. This was done, in fact, by Michael. This was done using polarimetry, because you can also do polarimetry with this instrument. So by observing, in fact, the earthshine, which is reflected from the moon, they were able to show the polarimetry signal of vegetation on the Earth. And so they could confirm that there is indeed life on Earth. So, I mean, it's always a good thing to have confirmation in science. But of course, we knew that. So, but the instrument is also used to do, for example, transmission spectroscopy of exoplanets. And this is some example of likers that you can obtain. But if you use the multi-object spectroscopy, you can do that in, of course, as a function of wavelengths, because you use the spectra. And then, in fact, you can measure the transit depth as a function of the wavelength. And this gives you indication about the structure of the atmosphere and the composition of the atmosphere of the exoplanet. And this is one example here, where there is the first time detection of titanium oxide in the atmosphere of an exoplanet. So the little brother of FORCE is EFOSC. It's the little brother, but in fact it's older, because it was there before. And it is attached to the NTT. It has a slightly smaller field of view, 4.4 arc minutes. But if your targets are not so faint, it may still be useful to go and use the NTT for these kind of things. So it can, of course, do very nice images. This is the interacting binary ARP271. And here are some example of planetary nebula images that were obtained, in fact, 2 weeks ago by students of the last year Neon School. And they took those images at the NTT, so rather nice. But you can, of course, also do spectroscopy. So here is an example of a young star in M17, the spectra, where you can clearly see the H-alpha profile and many different lines. You can also do multi-object spectroscopy with this instrument, and you can do polarimetry. So again, it's a very nice instrument to do many different things. And it is mostly used by the PESTO survey, who are trying to classify transient in the southern sky, and is one example of a type 1a supernova that was observed with EFOSC through the PESTO collaboration. So the NTT has another instrument, which is SOPHI, which is stands for Son of Isaac. And in fact, Isaac is a former instrument on the VLT, but is now decommissioned. So in fact, Sophie has lost his father. This is again, this instrument is now working in the infrared, and it can do also imaging with broadband and narrowband filters, but also spectroscopy at various resolution. And here is again an example from Pesto, because it's very easy. Like on the VLT, you can easily switch from one instrument to the other. On the NTT, you can also switch from EFOS to SOFI. So depending on what you want to do, you can observe in the infrared or in the visible. And so that's why Pesto will choose different instruments for that. You can also do polarimetry with SOFI. And one of the nice things about SOFI is that you can do high time resolution imaging with very, very short exposure times. And so this is again very useful to study transits. So here is an example from Valentin Ivanov, where you see the transit of an exoplanet. When you, this was exposure time of 0.6 seconds, so very short exposure times. And when you bin the data, you get an RMS of only 1.6 millimagnitude. So very impressive. So next to the NTT, we have the 3.6. And the 3.6 for the moment is hosting one instrument, which is ARPS, which is basically the exoplanet hunter. Even so, of course, it can do many different things, but it was mainly built for that. And the advantage of ARPS is that it is very, very stable. And it has a very high resolution power, more than 100,000. So it has been built to have very good radial velocity accuracy, which is indeed of about 0.5 meter per second on the short term. And over the very long time, in fact, it's also very good to keep this accuracy. And so people have measured 1 meter per second accuracy over more than 2 years. This is, of course, for rather bright targets, if you want, but you can still observe targets up to magnitude 17 with this instrument. And then you can still have radial velocity accuracy of 100 meters per second. So this is one of the nice examples coming from ARPS. It was the discovery of, at the time, it was not clear whether it was 5 to 7 planets into this system. Here, in fact, now 6 of them are completely secure. And you can see the signal obtained by radial velocities and the peak in the parallelogram. So this is a very nice example of what come out. And of course, one of the most famous examples coming from ARPS is maybe Proxima b. Here you can see the velocities as a function of the phase. And the semi-amplitude of this planet is only 1.4 meter per second. So I mean, it's really very, very tiny signal to discover. And there were many data obtained before by UVES and by ARPS, but because the star is an M dwarf, it is very active. And so there is a lot of signal that is adding onto the radial velocity signal. So it's very hard to see it. But when they really targeted the target, they managed to really see the nice presence of a planet, which is a planet with a period of 11 days and a minimum mass of about 1.3 times the mass of the Earth. And it is located in the habitable zone of this planet. So it is a very interesting object. And of course, it is very close to us. So the big brother is Expresso. This one we go back to Paranal now. So Expresso is going to be offered soon. In fact, it is undergoing commissioning for the moment. And this one is also going to follow the same principle as ARPS. And so again, here the idea is to go to even better precision, so up to 10 centimeter per second when you use one telescope. But there is also the possibility to combine the 4 telescopes together if you are interested in very thin targets. But in that case, your precision is only going to be only 1 to 5 meters per second. Okay, so this is coming soon, and I cannot give you results yet. So staying in Paranal, we have other spectrographs there as well. The oldest is UVES, so this one is also as old as force on the VLT. This is an HL spectrograph that has both a blue arm and a red arm that you can obtain simultaneously. So you can cover this wavelength range in one go if you want. And it has a spectral resolution nominal of 40,000, but you can also use a smaller slit and go up to 100,000 in spectral resolution for this instrument. What is important to realize is also is that for many of the instruments in parallel, we have what is called the rapid response mode. And this will allow, in fact, the telescope basically to go to the position of an object without any human intervention. So this is done fully automatically. If somebody has been granted a program to do these kind of things, he just has a code to activate. And if he activates, automatically the telescope goes there and start the observation. So this allows to do really observation within minutes, really a few minutes from the discovery of a transient object. And this is why this is mostly used for gamma ray bursts and trying to really observe them as soon as possible. But they were, of course, also used for kilonovae and for the gravitational waves objects, and to make sure to get them as soon as possible. This is one result obtained with UVES. This is an 8-hour spectrum of a very distant quasar. And in fact, they could use the quasar simply as a light probe, and then they can measure everything that is on the way. And they could detect CO molecules, which are 11 billion light years away. And this allows them to measure the temperature of the universe at this epoch. And they found that it was 9.15 degrees Kelvin, which is in excellent agreement with what is expected from the Big Bang. This is another example. This is mostly what UVES will do to do spare stellar spectroscopy. So here you can see, maybe you can see. So you can see the UV spectrum of a star, which is extremely metal poor. So basically there is nothing in this star except helium and hydrogen and a little bit of heavy element. And this star is thought to be about 13 billion years old. And they could really analyze it in great detail to determine the composition. Here it's also a nice transition because this is the UV spectrum, very detailed, so obtained at a resolution of 40,000. And on top of that, you can see the equivalent for X-shooter spectrum, which is obtained at a resolution of about 10,000. So X-shooter is another HL spectrograph, but the big advantage of this one is that you can really observe from the UV to the near infrared. So you have everything in one go. So this is very interesting for many different objects, and a resolution which is comprised between 4,000 and 17,000. So it has 3 arms in the UV, the visible, and the near infrared. And here is an example of what you can do. So here is really this huge wavelength range that is probed by X-shooter, going from the visible to the near infrared. And this is the spectra obtained by X-shooter over a few days after the discovery of the gravitational waves, which were originating from the colliding of 2 neutron stars. And you can see how the spectrum is changing with time. And this allowed the astronomers to infer how much air process elements were produced in this object. Another instrument that is sitting at the same telescope as UVES is FLAMES. And this one is a multi-fiber robot. So it's a very impressive machine. In fact, it's also huge. And we have to make sure that nobody enters this room, because if you are crushed by the plates, well, that's the end of you. So, and it observes in the visible with typically fibers up to 100 fibers, which can go to the giraffe instrument, but you can also link it with UVES up to 8 objects. So depending which object you want to study with high or low resolution, you decide where to put your fiber. And you can also use integrated field spectroscopy on a very small area. So here is the typical example of what flames will be used for. It is a globular cluster. So in this case, it's an NGC 6752 because flames has a field of view of 30 arc minutes. So you can then, in one single exposure, a spectra of 130 stars, which they did here. So they could observe, in fact, 130 stars of this globular cluster. And these globular clusters, like most globular clusters, are known to have two populations of stars, which are in fact separated by the abundance in sodium. And what they discover is that, in fact, all the AGB stars, so the ones which are really at the end of the life, are only belonging to the first population. So there is not a single AGB belonging to the second population of stars. And so they claim that this means that for the second population of stars, for some reason, the evolution of the star is already terminated at the RGB and does not go through to the AGB. So another multiplex instrument that we have is MUSE. I mean, this is also very impressive. Really, I mean, for those who have seen the Matrix, it may remind you some things. Not very nice. But this is in fact comprised of 24 spectrographs. And each spectrograph, I mean, each field of view is also even further split by 48. So in total, we have the equivalent of 1,152 minislits in the field of view of MUSE, which is 1 by 1 arc minute. And the resolution is typically about 4,000. And since very little time, we can also use it with adaptive optics if needed. So this means that when you observe with MUSE, you have an image in a 1 by 1 arc minute, but at basically every point of this image, you also have a spectrum. And so you can really do three-dimensional science. And you can start to see things that were not seen before. So this is a Redshift 5 galaxy. So this is observed by Hubble. Here are two different wavelengths, and you can see nothing. This is in the continuum of MUSE, and again, you don't see anything. But again, because you have a spectrum, in fact, at this location as well, if you look at the image corresponding exactly to the wavelengths, where there is Lyman alpha, which has been redshifted, well, you can detect clearly the galaxy. So you can use this instrument, and this is one of the main reasons why it was built, to really study faraway galaxies. But you can also do 3D studies. So this is the well-known pillars of creation, so M16. So we all know the very nice HST images that were obtained from this region, but like every image, those are 2Ds. Here again, in every point of this image, we know of a spectra. So you can use the spectra, compare that with models, and you can in fact infer the three-dimensional structure of this structure. And you can see that what looks like it was just part of one single blob is in fact 3 or 4 different blobs, and some of them are in front of the others. So there is really a 3D structure there, which you can only find out by using spectroscopy together with the imaging. And they could also study the evaporation of those structure, and that's why they estimate that the lifetime of this structure will be about 3 million years. This is another example taken by Andrena Mener from ESO. So she observed, in fact, the vicinity of a B bracket E star, which has this huge nebula, and this star lies inside the cluster with this very fancy name. And in fact, again, for every star in this cluster, we have in fact a spectrum. So this means we can do spectral classification, we can measure the extension, we can measure the magnitude, and we can put them into an HR diagram, which is shown here. And so, and then comparing with isochrome, you can also define the age of this cluster. So you can really get information that you would not get easily otherwise. And in this case, we found that this cluster has an age of about 3 million years. The other multi-object instrument we have is CMOS. This is the octopus of Paranal, but you have to imagine that instead of 8, it has 24 arms, and they are all cryogenic, so they are very cold. And each of those arms is again an integrated field spectrograph. So this is how it looks in reality. It's not as nice as the cartoon, unfortunately. And you can see that each of them has this little arm. This is a little mirror that will then, in fact, image a small area, which is 2.8 by 2.8 arc seconds, and for with 0.2 by 0.2 pixels. And so for each of the pixels in this little area, and for 24 of those, we will have, in fact, spectra. And so this allows to, in fact, study very distant galaxies. This is here the kind of things you can do. Those are HST images of very distant galaxies. So those are the images. This is the integrated stellar light. And then using CMOS, in fact, you can look at each pixel, the intensity of a given line, so like H alpha, and you can determine where the star formation is happening in those galaxies. But you can also use the spectroscopic information to measure the radial velocities and infer then really the kinematics of your galaxy. So you can really get three-dimensional information about those structures. Another imager that we have in Paranal is HawkEye, which stands for the High Accuracy Wide Field K-band imager. So this is a near-infrared imager with, again, the field of view similar to FORCE, 7 by 7 arc minutes, and a pixel scale of 0.1 arc seconds. And those are the typical limited magnitude, so about 24 in the GHK band. And it has, so those are the filters which are available on this instrument, so YJHK, as well as 6 narrowband filters, basically a methane filter, H2, bracket gamma, and 3 other cosmological filters. So this is the kind of image you can obtain with HawkEye. This is a gallery of spiral galaxies, but now they are observed in the infrared, and as Bruno said, you see something completely different when you observe in the infrared than in the optical, but it tells you the quality of the image we can get. And in fact, this quality is now even better because since last year, we have now an adaptive optics facility on UT4, which means that we have, in fact, what we call a deformable secondary mirror. So this is the mirror here, which has more than 1,000 actuators. So it can really react in real time to deformations. It also contains 4 laser guide stars, which are used by the instruments, and 2 modules for the instruments. So we have GRAL for HawkEye and Galaxy for Muse. And when you use this, this is what you see. So this is the image. It may be difficult to see it on the screen because unfortunately the screen has not the resolution of our telescopes. But this is the observation without the AOF, and this is with the AOF. In fact, I mean, if you blink from one to the other, you will see clearly a difference. This image is much sharper, and we can also see much deeper with this because we can really reach 0.2 arc second resolution. The other instrument that we have also in the infrared, but this time in the mid-infrared, so we go even further in the infrared, is Vizier. And this goes observed in the N band and the Q band, and it can do imaging and spectroscopy. So this is a typical pixel scale because, of course, in that regime we are diffraction limited, and the field of view is 36 by 38 by 38 arc second or 60 arc second square, depending on the pixel scale you choose. And the spectroscopy, you can use a low resolution mode or high resolution mode. This is one example obtained with Vizier. So this is in fact observation of Neptune. And you can see that if you observe in a given wavelength that is going to be sensitive to the troposphere, we see in fact the source pole of Neptune, which is hotter by about 10 degrees than the rest of the planet. We see, if we look now in the different band, we see that this pole is slightly shifted. And this is in fact the indication that this hotspot is also from where methane is escaping from the planet. And here it's observation at 2 different times, and you can see how this spot is rotating with the planet as well. Here's another example, this time observing a yellow hypergiant. And with Vizier, it is possible to discover, in fact, 2 double shell, which are huge and very dusty, in order to be able to see them in the infrared. And that's why Eric Lagadec called it the fried egg nebula. So going now to adaptive optics instruments, the next one is Naos Konica, or NACO for short, which again is in the infrared, but it's an adaptive optic instrument that can do imaging, polarimetry, coronagraphy, and spectroscopy. What is very interesting for this instrument is that it has an infrared and a visible wavefront sensor. So this means that if you have a star as a reference, but which is very dim in the visible, but is visible in the infrared, you can use it. So this is very useful to observe, for example, in the galactic center, where there is a lot of dust. You don't see many stars in the visible, but in the infrared, you will see them. Thanks to this infrared wavefront sensor, you can do AO corrections. And those are the typical limits of magnitude. And also useful for this is that you can use a reference star which is off axis. So it does not need to be the same target, the same object as your target. So one of the first nice example coming out of this instrument was the first image of an exoplanet. And in fact, here, of course, it is an exoplanet. There is a lot of debate whether it's a real planet or not, because it's not orbiting a star, but it is orbiting another brown dwarf, which is 25 Jupiter masses. And the star is also very far away, 55 astronomical units from its companion. But still, it's a nice achievement, and it was the first time we could do these kind of things, thanks to NACO. But as I said, NACO is mostly used for the galactic center, because this is where really the infrared wavefront sensor can be of big use. And so this is an image obtained with NACO of the central part. And if you zoom in, this is the location of the black hole, Sagittarius A. And in fact, with NACO, they have been able now to really see the orbit of many stars around the black hole. And using simply Kepler laws, you can determine the mass of the black hole. So we know that it is about 4 million solar masses at the center of our galaxy. And one of the stars that have been most studied is S2, which is this one. And you can see we have observation with different ESO instruments already from 92. And the very interesting thing is that this one is the one coming closer to the black hole, and its closest approach is going to happen this year. And it will be very useful to try to probe the gravitational theory in high regime. So Symphony is another adaptive optics instrument that is also useful, but it's again here an integral field spectrograph. So you can do not only take image, but you take in fact also spectra using again AO. And in fact, this one will use a guide star, a laser guide star, in order to be able to look at any point in the sky. And this is the typical resolution you get. Field of view can be between less than 1 hexagon square to 8 hexagons square, and the typical magnitude. So again, here this was used to study the galactic center, but here Instead of it being simply images, for every point we have also spectra. So it was possible to classify the stars in the close vicinity of the black hole, and at the same time obtain their velocities, so measure radial velocities, which are then useful in order to determine their orbit. The most recent AO instrument that we have in Paranal is SPHERE. This is a high contrast imaging, low resolution spectroscopy, and also polarimetry instrument. And the idea of SPHERE is to be able to do extreme adaptive optics. So we aim to do to reach a Streller ratio which is higher than 75% in the H band. So this is much better than what NACO, for example, can achieve. The only problem with SPHERE is that you need to have an on-axis reference star, and it will be in the visible, and the magnitude of this star has to be brighter in the R band than 13. So we cannot use, for example, SPHERE to study the galactic center. And the field of view is written down here, so up to 11 by 11 arc seconds. This is the kind of things you can do with SPHERE. So this is an high contrast instrument. So the idea is to be able to detect planets around the star. And of course, it is using a coronagraph in order to try to get rid of most of the light from the star. And this is a well-known system, HR 8799. And you can see that with SPHERE, we easily detect the 4 planets around this system. But you can also do some other things. This is imaging of a protoplanetary disk with SPHERE, and you can see the very nice spiral structures. And the origin of that is still debated, whether it is due to the presence of a planet or whether it is simply some reflection effects. But still, it provides really incredible images. And this is another example. This is comparing with HST. So this is the HST image of Io around Jupiter. And this is the same with SPHERE in the infrared. So you can see that we can achieve a better contrast even than Hubble with extreme AO. And you can also do not only planets, you can also do, of course, stellar astrophysics. This is a red hypergiant, and the SPHERE observed both in the V band and in the infrared. So you can use it to really take image in both things. And you can see these huge structures of mass loss coming out of this star. So this was for the normal instruments. But at ESO, we have also, in Paranal, we have also the interferometer. So with the interferometer, we are combining the light of 4 telescopes. And this can be done either by using the 4 smaller auxiliary telescopes, or we can use also the 4 big UTs. The advantage of the small 4 auxiliary telescope is that they can be moved around, so you can have a different coverage of the UV plane. Pioneer is one of those instruments. It was initially a visitor instrument on Paranal, but now it is an ESO instrument. And it is a very efficient instrument that allows to use those 4 telescopes. And you can typically have a full calibrated sequence in less than 45 minutes and get very nice results out of it. So what kind of thing you can do is, for example, measuring the size of stars. Christian Hummel is tomorrow going to explain you in more detail what interferometry does. But basically, we are using, if we are using visibilities, we can simply fit that to uniform disk and obtain the diameter of the star, which was done in this case here for 6 symbiotic stars, and you can determine really the radius and place them again into an HR diagram and understand why those stars are having mass transfer. You can also, oops, this didn't come out very nice. This is the transfer from Mac to PC Windows. Sometimes it does something strange. But you can use also the interferometry in order to detect the companion and to then measure very precisely the orbit of those companions. So this is done here. So for the 3 stars, when you can see the orbit that we could obtain with interferometry. And if you combine that with the spectroscopic orbit from those systems, in fact, you have all the information in order to get the masses of those stars in the system, so the Bose masses. And you can achieve 1% or even better precision on the masses of stars. So this is very important to calibrate stellar evolution models. And the most latest addition to the interferometer at ESO is graphite. So this one is again a 4-beam combiner, but unlike Pioneer, which is observing in the H band, this one is observing in the K band. And this one is also doing spectroscopy, and you can choose between low or medium resolution spectroscopy. And the main science is again a study of the star in the galactic center. The idea is really to be able to probe, in fact, the closest approach of S2 towards the galactic center this year and try to infer as much information as possible about the black hole. But of course, you can use it for many different things. Here is one example. So what we have is, in addition to the phase and the visibility, we have also a spectrum, but the spectrum is resolved. And so this is a spectrum, in fact, of Eta Carina, of the winds of Eta Carina. And if you look at, in fact, along this line, which means you are probing the velocities, you can see different structures in the wind. And this really tells you about the complex morphology in the wind of this star. So this is really a unique instrument to do that. Okay, sorry. So I've shown you that we have many instruments in Lacia and Paranal. We have, in fact, 19 instruments that you can use. So basically, whatever your science is, you should be able to find an instrument that will fit it. And please do so. Thank you very much.
Are there any questions? No? Are you sure?
I'm very clear.
All right.
Okay,
question from people online? Yeah, go for it.
Hello, this is Stuart Ryder here. Thank you very much, Henri, for a very comprehensive overview. I would just like to go back to, I think, one of the first slides you showed talked about the VeriCam instrument on Vista. And I think you mentioned the wavelength coverage was only to 1.2 microns. I would have thought...
yeah, apparently I made a mistake. When I saw the face of Marina, I understood I made a mistake there.
Ah, so it should be 2.5.
Correct.
Okay, thank you.
VeriCam has a Z, Y, JH, and K band filters and a few narrow band filters, but essentially it goes to 2.2 micron.
Right, thank you.
Any other question? Okay, so